All right. Hello, everyone. Let me take the lecture videos for the 12th week of this spring semester. So I was planning to cover three topics this week. Um, so two remaining topics in chapter 11 and introduction of chapter 12. So one introductory section of chapter 12. But let me do this. So let me introduce chapter 12 in the live lecture. So I'm just going to take two videos for just these two topics in chapter 11. Okay. So in this video, I'm going to introduce the characteristic root test for sine definiteness. So the basic idea of this test is, so we are going to study one more test for the sine definiteness. So remember, in the previous week and previous video, we studied how to maximize or minimize a multivariate function. So if the function, the objective function, depends on several variables, the optimization condition is slightly different from the derivative test, which we adopted for single variable functions. So the first order condition requires all partial derivatives should be equal to zero at the extreme value. And the second order condition requires Hessian matrix is either positive or negative definite. Right? So we studied a simple criterion for determination of this sign definiteness. So whether Hessian matrix is a positive or negative definite. So remember, if function depends on two variables, so if we work with a function f of x and y, its associated Hessian matrix takes this form. So consisting of the four second partial derivatives. So the way to determine the sign definiteness of this Hessian matrix, we used principal minors. So if the first principal is positive and the second principal, that is the determinant of this 2 by 2 matrix, is positive. So all principal minors are positives, then Hessian matrix is going to be positive definite. But if the sign alternates, so this guy f sub xx is a negative, but the determinant of this 2 by 2 is positive, then Hessian matrix is going to be negative definite. Okay? And in this video, we are going to study one more test. So one alternative test for this sign definiteness. So it tells us whether Hessian matrix is a positive or negative definite. But this time, instead of these principal minors, we are going to utilize the eigenvalue. Okay. So the eigenvalue is one of the most important topics in linear algebra. So we should have studied this early semester, but somehow this eigenvalue is introduced in chapter 11 in relation to optimization. So I decide to postpone that. So I decide to postpone the discussion, the relevant discussion to chapter 11. Okay. So in order to understand the eigenvalue exactly, we have to spend at least 1 week because that is a very important topic. But we just have a limited time until the end of the semester. So let me just introduce the definition of this eigenvalue. So what is the eigenvalue and what is this eigenvalue for in the optimization problem? So how it is applied to determination of the sign definiteness in the optimization problem. Okay, so in order to illustrate this eigenvalue in the simplest setting, let me work with 2 by 2 symmetric matrix. So matrix A is given by this 2 by 2 matrix A and C and B. Okay, because we have a symmetry on matrix A, these two off-diagonal entries are equal to each other. Okay, so we have this. We have a matrix A of this form, and the eigenvalue is denoted by lambda. So this is a green letter. We call this lambda. So we are going to use the same letter for the Lagrangian multiplier in the live lecture, but the common notation for eigenvalue is this green letter lambda. Although the textbook uses some different notation for this eigenvalue, let me stick to the common notation. Okay. And then the definition of the eigenvalue is a solution to the following matrix equation. Okay. So in this equation, we have a times x on the left and lambda times x on the right. Okay, so in order to characterize this equation, we have to use one more vector. So that is a non-zero vector. Let me highlight this, non-zero. So for some non-zero vector x, we have identical expressions in this equation. Okay. So this non-zero vector is called eigenvector. Okay. So the eigenvector always accompanies eigenvalue. Okay. In the sense that we can find one eigenvector to corresponding to eigenvalue, and vice versa. We can find one eigenvalue corresponding to one eigenvector. Okay, so they are companies of each other. Okay? And both of them characterize this equation. Okay? So one major law of this eigenvalue is so take a look at this equation. On the left, we have matrix multiplication. So because we are working with a 2 by 2 matrix, so the matrix A's dimension is 2 by 2. So for the conformability condition, for this matrix, for this multiplication to be well defined, vector x should be 2 by 1. It has dimension. It must have dimension 2 by 1. Okay. Then after multiplication, we're going to have 2 by 1 vector on the left, and then eigenvalue is a constant. That is a scalar. That is a one number. Okay, so we have a scalar multiple on the right. Okay, so the dimension of this lambda x is going to be the same as the dimension of vector x. So it is also 2 by 1. Okay, so unless the dimension-wise, this equation is well defined. Okay, so the major role of this eigenvalue is to transform this matrix multiplication into scalar multiplication. Okay, so it summarizes the matrix A, that is a 2 by 2, right? This 2 by 2 matrix, into one number. Okay? So that is a major role of this eigenvalue in linear algebra. Okay? So it can be used for many different objectives, but we are going to focus on this sine definiteness test. Okay. Right, so in order to find lambda from this equation, let me use identity matrix. So let me put the identity matrix in the middle on the right. Okay, because identity matrix does not influence the product, the matrix multiplication. So after putting the identity in the middle and moving this term to the left, and I have then common factor x, and factoring out that x and putting in the back, so I obtain this one on the left side. Okay, then I'm left with a nothing on the right. Okay, so I have a 2 by 1 zero vector on the right. Okay, so remember the dimension of this equation is 2 by 1. So not just a number 0, we must have 2 by 1 zero vector. Okay, and the dimension of vector x is 2. We have x1 and x2. Okay, so after rewriting this equation in this form, now the equation can be seen as a homogeneous equation. Okay? So regarding this, A minus lambda I as a coefficient matrix, and x as the variable matrix, and 0 is a constant matrix, now it can be regarded as one homogeneous equation. Okay. Now remember, so now this is a solution to this equation. But we have a non-zero solution. It means, this homogeneous equation has non-trivial solution. Okay? And remember the sufficientness, we studied several conditions for non-trivial solutions in homogeneous equation. So, for this homogeneous equation to have non-trivial solution, the coefficient matrix must be non-invertible. Okay, so in other words, it must be singular. Okay, so in other words, the determinant of this coefficient matrix must be zero. If this matrix is invertible, okay, was a invertible, then this homogeneous equation must have a one unique solution that is a trivial solution. Okay? So x1 and x2, both of them should be equal to zero. But we have a non-zero solution from this equation, right? So the corresponding coefficient matrix must be non-invertible. All right, so with that in mind, now using this form, matrix A, I can rewrite, so I can formulate the coefficient matrix as, so into AC and C and B minus scalar multiple of identity matrix, so lambda 0 and 0 and lambda. So their difference can be written as A minus C or A minus lambda, and the C in the first row. And in the second row, I have C and B minus lambda. Okay. And to repeat, the determinant of this matrix should be equal to 0. So A minus lambda times B minus lambda minus C squared should be equal to 0. Okay. So this brings me to the following quadratic equation, okay, in terms of lambda. Okay, so I can solve this equation when A, B, C are given. Okay, so to identify the eigenvalues. So in linear algebra, this equation is called the characteristic equation. So another way to define eigenvalue lambda is the solution to this characteristic equation. So for this reason, eigenvalue is often referred to as the characteristic root. So characteristic root is the another name of the eigenvalue. So eigenvalue and characteristic root indicate the same thing. All right. So yeah, you can easily imagine that. So you can easily anticipate. So now, so in this example, we worked with 2 by 2 matrix. But if we worked with a 3 by 3 matrix, then the determinant, so the determinant of this coefficient matrix is going to be cubic equation, right? But in case of m by n, the characteristic equation is going to be nth order equation. Okay. So with that, so except that difference. So here the definition and the way to find the lambda eigenvalue is exactly the same. Okay? So let me just restrict attention to this 2 by 2 case. Right. So now using this example, let me illustrate how to find the eigenvalues and eigenvectors. Okay. So we have this 2 by 2 matrix. Sorry for my croaky voice. All right. So the way to find eigenvalue is we have to start with the construction of this characteristic equation. So A is given by this 2, 2, 2 minus 1. And we subtract away this lambda I. Okay. So I just try to construct this coefficient matrix in this example. So lambda 0 and 0 and lambda. So I have 2 minus lambda and 2 and 2 negative 1 minus lambda. Okay. So its characteristic equation is, now we have to compute the determinant of this 2 by 2 and set it equal to 0. Okay, so 2 minus lambda multiplied by negative 1 minus lambda minus 4. The product of these two off diagonal entries and set it equal to 0. Okay. So now we encounter one quadratic equation in terms of lambda as expected. So solving this equation for lambda, so first distributing 2 minus lambda, I obtain lambda squared minus lambda minus 2 minus 4 that is equal to 0. So lambda squared minus lambda minus 6 equal to 0. So from that, I obtain two distinct solutions. So two distinct eigenvalues, either 3 or negative 2. Okay, so that is the way of finding eigenvalues from the given matrix. Okay, so this part is doable, I guess. And the way of finding eigenvectors, that is kind of irrelevant to our course material, but let me illustrate how to find eigenvectors, okay? So we have two eigenvalues, and each eigenvalue results in different eigenvectors. So let me first characterize the eigenvector corresponding to the first eigenvalue. So in case of 3, so when lambda is a 3, now the coefficient matrix is going to be negative 1 and 2, and 2 and negative 4 in the second row. So this is going to be coefficient matrix of this homogeneous equation. Right? So the homogeneous equation can be stated as negative 1, 2, and negative 4, and variable matrix x1 and x2, that is a zero matrix. Okay, so now solving this equation, so let me first compute this multiplication. And I have negative x1 plus 2x2 as the first entry, and the second entry will be 2x1 minus 4x2. So that is 0 and 0. Okay, so the first equation gives me x1 equals 2x2. The second equation gives me 2x1 equals 4x2. Okay, so now you can easily verify that the second equation is just a multiplication. So the linear combination of the first. Okay, so these two equations. So one equation is just the duplicative of the second, right? So one equation is redundant. That comes as no surprise. By the definition of eigenvalue, we make this coefficient matrix be singular. Okay, so just in this case, we have a non-trivial solution, right? X1 and X2. So we have a non-zero vectors X1 and X2. That satisfies this given equation. All right, so any pairs of x1 and x2 satisfying this relation, so x1 is 2x times 2 times x2, can be seen as a solution, so can be put as a solution to this homogeneous equation. So for example, if x1 is 1, then corresponding x2 is 1/2. So it is a solution to this equation, and 2 and 1, and 3 and 1.5, and 4 and 2, and so on. So we have infinitely many solutions to this homogeneous equation. Okay? But so these are candidates of eigenvectors, right? So eigenvectors are, defined as this, solution to this homogeneous equation. But among them, we are going to focus on one special type of eigenvector. So that is, you know, uh, with a size equal to one. So when we have a 2 by 1 vector x1 and x2, the magnitude of this vector is defined as x1 squared plus x2 squared. Okay, so 2 comma 1, its magnitude is square root of 5. Its magnitude or size is equal to square root of 5. Okay? So it measures the how large this vector is. Okay, but we normalize, so among them, we focus on one eigenvector whose magnitude is equal to 1. Okay, so this process is called normalization. Normalization. So we normalize the size of the eigenvector equal to 1. Okay, right. So which vector has a which vector does have so which vector has a just magnitude 1? If you think about this problem, so let me put x1 as a k. Okay, then x2 should be k over 2, right? So I just relabel variable x in terms of some constant k. Okay, so now if we think about k comma k over 2, okay, its magnitude is going to be k squared plus k squared over 4. Okay, now we would like to normalize this to 1. Okay, and now solving for k gives me gives me the value of x1 and value of x2 as well. Okay, so from that we can identify unit eigenvector. Okay, so unit eigenvector. So that is a eigenvector with a size 1. Okay? So solving this equation for k, I obtain 2 over square root of 5, I guess. Okay, so x1 is going to be 2 over square root of 5, and x2, that is given by k over 2. So 2 over square root of 1 over square root of 5. Okay, so that is the way to compute unit eigenvector. Okay? All right. So let me leave for exercise. Finding eigenvector or unit eigenvector corresponding to negative 2. Yeah? All right. So now the main result in this video is, so it turns out that eigenvalue can be used to determine whether given matrix is a positive or negative definite. So now using this eigenvalue, we can tell whether given matrix is a positive or negative definite. So the theorem states that matrix A is a positive definite if all eigenvalues are positive. Okay, and matrix A is a negative definite if all eigenvalues are negative. All right, and then if some eigenvalues are positive and some eigenvalues are negative, then we can determine the sign definiteness. So the matrix is going to be indefinite. Okay. So in the previous example, we have one positive value and one negative value. Okay. So this matrix is indefinite, meaning that A quadratic form generated by this matrix may take a positive value or negative value, depending on this vector x. Okay. The proof of this statement is beyond our scope. We have to spend at least 1 week for the proof. But let me just present the basic idea of this theorem. So remember, the definition of the eigenvalue is, so it equates this matrix multiplication with a scalar multiplication. Okay, for some eigenvector, non-zero eigenvector x, right? And then let me pre-multiply x transpose here. Okay, then we obtain the quadratic form on the left, and on the right we have this, but lambda is a constant, so I can pull it out. And I obtain x transpose x. But if we think about x transpose times x, so in case of 2 by 2, so that is x transpose, and this one is the original vector x, 2 by 1, okay? And its multiplication gives me x1 squared plus x2 squared, okay? So no matter what this x, so first entry may be negative or second entry may be negative, does not matter. No matter what x, it is always positive. So this multiplication is always positive. Okay. So the sign of this quadratic form depends on the sign of lambda. Okay. So if lambda is a positive, then quadratic form takes a positive value. If lambda is a negative, then quadratic form takes a negative value. Okay. Of course, this is a just one part of proof because we have to show that originally this quadratic form takes a positive value for every non-zero vector, not just for eigenvectors, but we have to show that this takes a positive or negative value for every non-zero vector. Okay? But this process, so this part requires another material, the so-called diagonalization. So there is a very nice technique. Uh, so in linear algebra, so the way to diagonalize a given matrix. So the given matrix was just A, C, and C and B. And we can convert this into some diagonal matrix. So the off diagonal entries are 0, and we have some non-zero numbers on diagonal only. Okay. This part is also very important in linear algebra, and that is the main essence, the key essence of the eigenvalue. But due to lack of time, let me skip this. Okay, so just remember the this eigenvalue test for the sign definiteness. All right, so using this test, we can restate the conditions for extreme values as follows. So for function f, to have a extreme value at point A comma B, the two partial derivatives should be equal to 0 at this point. And now using this eigenvalue test, we can restate the second order condition. So the function will attain local max if the Hessian matrix is a negative definite. So if all eigenvalues of the Hessian matrix are negative. Okay? And the function will attain local minimum if the Hessian matrix is a positive definite. So in other words, all eigenvalues are positive. Okay, so that is a one punchline of this video. All right, so in this video, I explained the eigenvalue test for sign definiteness. So it tells us whether a given matrix is a positive or negative definite. Okay? So hope you find this video useful, and then I will take one more video after the live lecture.